My name is Jim Al-Khalili, and I'm a professor of physics at the University of Surrey. Studying the innermost secrets of atoms and their nuclei has been at the heart of my working life. But there's another side to me. I was born and grew up in Baghdad to an English mother and Iraqi father, but left Iraq with my family in the late 70s when Saddam Hussein came to power. By then, science was already my great passion in life, and as I studied it further, I saw myself fully part of the Western tradition, inspired by names like Newton and Einstein. But buried away was this nagging feeling that I was ignoring part of my own scientific heritage. I still remembered my school days in Iraq and being taught of a golden age of Islamic scholarship, that between the 9th and 12th centuries, a great leap in scientific knowledge took place in Baghdad, Damascus, Cairo, and Cordoba. So I want to unearth this buried history, to discover its great figures, and to assess exactly what their contribution to science really was. Are there medieval Muslim scientists who should be spoken of in the same breath as Galileo or Newton or Einstein? And crucially, what is the relationship between science and Islam? My journey into the science of the medieval Islamic world will take me through Syria, Iran, and North Africa. I started in the back streets of the Egyptian capital, Cairo, with the realization that the language of modern science still has many references to its Arabic roots. Take scientific terms like algebra, algorithm, alkali. I instantly recognize these words as Arabic. And these are at the very heart of what science does. There will be no modern mathematics or physics without algebra, no computers without algorithms, and no chemistry without alkalis. Surprisingly few people in the West today, even scientists, are aware of this medieval Islamic legacy. But it wasn't always so. From the 12th to the 17th century, European scholars regularly refer to earlier Islamic texts. I have here copies of some pages of the book Liber Abaci by the great Italian mathematician Leonardo Pisano, otherwise known as Fibonacci. What's fascinating is that on page 406 is a reference to an older text called Modum Algebra et al Muqabala, and in the margin is the name Mahomet, which is the Latinized version of the Arabic name Muhammad. The person he's referring to is Muhammad ibn Musa al-Khwarizmi. In fact, Arabic names crop up in many medieval European texts on subjects as varied as map-making, optics, and medicine. But I want to start with al-Khwarizmi because his work touches on a crucial aspect of all our lives today. It's thanks to al-Khwarizmi that the European world realized that their way of doing arithmetic, which was still essentially based on Roman numerals, was hopelessly inefficient and downright clunky. If I ask you to multiply 123 by 11, you may even be able to do it in your head. The answer is 1,353. But try doing it with Roman numerals. You'd have to multiply CXXIII by XI. It can be done, but trust me, it's not fun. Al-Khwarizmi showed Europeans that there's a better way of doing arithmetic. In his book entitled The Hindu Art of Reckoning, he describes a revolutionary idea. You can represent any number you like with just 10 simple symbols. The idea of using just 10 symbols, the digits from 1 to 9, plus a symbol for 0, to represent all numbers from 1 to infinity, was first developed by Indian mathematicians around the 6th century AD, and I can't overstate its importance. Let me show you. Here are the numbers in Indian Arabic numerals. 1, 2, 3, 4, 5, 6, 7, 8, 9. And here are the numbers we're more familiar with in the West. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see the similarity between these numbers, in particular, for instance, the digits 2 and 3. If I tip this sideways, you can see now how they look like numbers 2 and 3. And what's powerful about these digits, this numerical system, is how it's simplified arithmetic calculations. But Al-Khwarizmi and his colleagues went further than just translating the Indian system into Arabic. They created the decimal point. This text, written a century after Khwarizmi, is by a man we know only as Al-Uqlidasi. Here he shows that this same decimal system can be extended to describe not just whole numbers, but fractions as well. The infinity of possibilities that lie in between the integers. Here's a copy of Al-Uqlidasi's manuscript where he showed how the decimal point is used for the very first time. He describes it by using a dash. Here are the digits 1, 7, 9, 6, 8, and you can see there's a small dash over the 9 indicating the decimal place. The idea of the decimal point is so familiar to us that it's hard to understand how people managed without it. But like all great science, it's blindingly obvious after it's been discovered. The story of numbers and the decimal point hints that even over 1,000 years ago, science was becoming much more global. Ideas were spreading, emerging out of India, Greece, even China, and cross-fertilizing. And looking on a map that shows where people lived 1,000 years ago gave me my first insight into why medieval Islam would play such an important role in the development of science. Now look at which city lies at the center of the known world, a place where the widest range of peoples and ideas were bound to collide. It's the city where I was born, the capital of the Islamic Empire, Baghdad. Recent events mean I can no longer visit the city. But these are the home movies of my cousin Faris, filmed in the 1960s. The Baghdad we knew then looked nothing like the bomb-wrecked city it is now. I certainly grew up proud to be associated with one of the world's greatest cities. Baghdad was founded in 762 AD by the Caliph al-Mansur. His aim was to make it the glorious capital of a brand new empire, united by Islam, the rising religion of the time. The Abbasid caliphs had claimed their right to rule by declaring that they were directly related to the Prophet Muhammad, who had founded the new religion over 100 years earlier. But in that short time, the armies of Islam had conquered a vast territory. Starting in a small area around Medina, they moved rapidly out of the Arabian Peninsula and within a few decades had taken control of the Levant, North Africa, Spain and Persia.
I think one must bear in mind that this is an era in which people actually believed in God, and the dramatic successes of the Arabs as they poured out of Arabia was such that a lot of people did sort of observe and say they must have God on their side, this must be the true God. Some people did convert, or if they didn't convert, they did submit to Arab Muslim political control for that reason.
By the early 8th century, Islamic caliphs ruled a vast territory. And like most successful emperors, from Caesar to Napoleon, they understood that political power and scientific know-how go hand in hand.
There were many reasons for this. Some were practical. Medical knowledge could save lives. Military technology could win wars. Mathematics could help deal with the increasing complexities of the finances of state. And Islam as a religion also played a pivotal role. The Prophet himself had told believers to seek knowledge wherever they could find it, even if they had to go as far as China. And many Muslims, I'm sure, felt that to study and better understand God's creation was in itself a religious duty. But there were also other less edifying motives at play. To many in the ruling elite of the Islamic Empire, knowledge itself had a self-serving purpose, because possessing it was seen as proof of the new empire's superiority over the rest of the world.
But with military and political success, the Islamic caliphs faced an inevitable problem. How do you sensibly govern a hugely diverse population? Although some of the empire had converted to Islam, they were still separated by huge distances and adhered to many different traditions and languages. In the 8th century AD, the empire's leader, the Caliph Abd al-Malik, had to find a way of administering this mishmash of languages. Like all the great figures of the Islamic Empire, Abd al-Malik lived in a culture without portraiture. All we have are later impressions of what he might have looked like. His solution was sweeping in scale and inadvertently laid the foundations of a scientific renaissance.
It was this Abd al-Malik ibn Marwan who said, this bureaucratic chaos has to stop. We cannot continue to run a government and govern all of this span of land with this Tower of Babel languages. So he wanted to govern it with a uniform language. That uniform language, of course, he wanted to be able to understand it, so he demanded that it be in Arabic.
But the choice of Arabic as the common language of the empire went beyond administrative convenience. The decision had extra force and persuasiveness because Islam's holy book, the Quran, is in Arabic, and Muslims therefore consider Arabic to be the language of God. The words of the Quran are so sacred that its text hasn't changed in over 1400 years. By comparison, English has changed dramatically in just 700 years. To our ears, Chaucer is almost unintelligible, whereas any Quran can be understood by anyone who reads Arabic. Making copies of the Quran has always been a specialized and highly respected job since the foundation of Islam. Calligraphy expert Naif Scarf, who lives in the Syrian capital Damascus, writes for mosques and in madrasas all over the country. These are words he's found himself writing over and over again, words of great significance for Muslims. They're the opening line to each chapter in the Quran.
So what it says is, Bism illah ar-Rahman ar-Rahim.
which means in the name of God, the most gracious and the most merciful.
بده يشكل مضبوط الفاعل المفعول بكذا ليكون الكتابة صح ولا تفهم المعنى بشكل صحيح.
So you're saying the complexity of Arabic calligraphy was enforced on them because of the spread of Islam, because they were worried the meaning of the words in the Quran would be lost if it was read by people who don't speak Arabic. Then they wouldn't, not only would they misinterpret it, they just wouldn't be able to distinguish between different letters. So not only did they add dots on certain letters, they also added other little squiggly lines which changed the sound of vowels. And it was something that they put in place just to ensure that people were able to have the right pronunciation when they read the Quran. The consequences for science were immediate. Scholars from different lands who previously had no way of communicating now had a common language. And it was a language that was specially developed to be precise and unambiguous, which made it ideal for scientific and technical terms.
What this meant was the summoning into existence of a vast intellectual community where scholars from very different parts of the world could engage in dialogue, comparison, debate, argument, often very fierce argument, with each other. It was possible for scholars based in Cordoba in southern Spain to engage in literary and scientific debate with scholars from Baghdad or from Samarkand.
But I can tell you that scholars aren't motivated by the love of knowledge alone. There's nothing like a large hunk of cash to focus the mind. By the early 800s, the ruling elite of the Islamic Empire were pouring money into a truly ambitious project, which was global in scale and which was to have a profound impact on science. It was to scour the libraries of the world for scientific and philosophical manuscripts in any language. Greek, Syriac, Persian, and Sanskrit. Bring them to the empire and translate them into Arabic. This became known as the translation movement. The effort scholars put into finding ancient texts was astonishing. And one key reason for this is that bringing a book to the caliph, which you could add to his library, could be extremely lucrative.
The story goes that the Caliph al-Ma'mun was so obsessed that he would send his messengers out of Baghdad far and wide to distant lands just to get hold of books that he didn't possess for the translation movement. And anyone who brought him back a book that he didn't have, he'd repay him its weight in gold.
To give some sense of the extent of this activity, sort of between 750 and 950, somebody called An-Nadim, who wrote a list of sort of the intelligentsia of the Abbasid era, lists 70 translators. So it was quite a large cohort of people involved in translation, and obviously he only named the well-known. They could get up to 500 gold dinars a month, which is probably around $24,000, which is a huge sum of money for what they were doing. It was a very, very prestigious, well-paid, well-patronized activity.
And motivating this global acquisition of knowledge was a pressing practical concern, one that rarely crosses our minds today. This is the new library at Alexandria in Egypt. But fresh in the memory of many in the empire was the story of the destruction of the original library at Alexandria centuries earlier, and the shocking loss of thousands of years of accumulated knowledge.
One of the things that we tend to forget, because we live in an age of massive information storage and perfect communication, more or less, is the ever-present possibility of total loss. That was very, very important for medieval Islamic scholars. They knew extremely well that writings could be forgotten or buried or burnt or destroyed, that cities could pass away. And what we see in Baghdad or Cairo or Samarkand is exactly the gathering together, translation, analysis, accumulation, storage, and preservation of material that they were well aware could be entirely lost forever.
And if there was one branch of knowledge that everyone, from the mighty caliph to the humble trader, wanted to preserve and enhance, it was medicine. These were, after all, times when few lived to old age. Writings from the time remind us that what we might consider a relatively minor infection today could be a death sentence. Religious teachings, then, were not just a source of comfort. They were a constant reminder that we should never give up.
In the Hadith, which is the collected sayings of the Prophet Muhammad, it says, "Ma anzala Allahu da'an illa wa anzala lahu dawa'an," which means that God did not send down a disease without also sending down its cure.
It's statements like this that lead Muslims, even today, to believe that cures for all diseases are out there somewhere, and that we need to search to find them. To assess how this optimism actually affected Islamic medicine, I met up with Dr. Peter Porman in the Syrian capital, Damascus. He's a leading expert on Islamic medicine who spends much of his time researching here in the Middle East.
What people don't realize is that the history of Islamic medicine is really the history of our medicine, because our medicine, the university medicine we used until the 19th century, it was based to a large extent on all these work of these Islamic physicians.
Islamic medicine built extensively on the foundations laid by the ancient Greeks. The most highly prized and among the first to be translated into Arabic were the medical manuscripts of the 3rd century Greek physician Galen.
Galen believed that a healthy body was one in balance, a balance of 4 types of fluids called humours, which circulate through the body, and any one of which, if out of balance, would cause illness and a change of temperament. The 4 humours were yellow bile, which, if in excess, would cause the patient to become bilious or bad-tempered and nauseous. Blood, too much of which would cause the patient to become sanguine or cheerful and flushed. Black bile, which in excess would cause the patient to become lethargic, melancholic, even depressed. And phlegm, which in excess would cause the patient to become phlegmatic or apathetic and emotionally detached. Galen argued that illnesses are caused by an imbalance in one of the humours, and so the cure lies in draining the body of some of that humour. And so he recommended techniques like cutting to induce bleeding or using emetics to induce vomiting.
But Islamic doctors were acutely aware that Galen and Greek medicine were only one source of medical knowledge. There were other traditions of medicine that they were equally keen to incorporate into their understanding of how the body functioned. Medieval Arabic texts refer to wise women, folk healers who provided medical drugs. This tradition continues today, as I found when I came across one for myself in the back streets of Hammamat in Tunisia. This is Arafat Nabil. She's been running her shop selling medicinal herbs and spices for over 20 years. She believes that her remedies can cure a wide range of medical ailments.
مثلا هذه عشبة اسمها شيح تنحى الدود من البطن وتنحي جميع الأوجاع الداخلية. بعد من الزرنيخ ينحي الثعلبة، وبعشبة هذه اللي تراها انت تويكا تنحي تقولوا البرص.
اوكي.
مثال هذوما مثلا كما هذه وهذه للصرع والجنون. صرع يحطها ويحط شويه في المخده نتاعو، ما عادش بك اللي يشدوا الكريز هذاك.
وفي يعني مثلا من العصر اليوناني اقدم منها ما تستعمل ولا لو؟
والله ايش نقول لك، كل ما هو قديم في الاعشاب انا نتبعه. فهمتني؟ باش نزيد معلومات.
In the back streets of Tunisia, this knowledge is still being used. But medieval Islamic doctors were also aware of other traditions of medicine from China and India. And yet another tradition of medical guidance came from within Islam itself, and takes some of its ideas from the Quran and some from the collected sayings of the Prophet, the Hadith. In a bookshop in Monastir in Tunisia, I found a copy of a very popular book, available right across the Islamic world.
This book is called The Prophet's Medicine, and see how old it is. The author was born between 691 and 751 Hijri, which places him in the 14th century. Here's an interesting bit where it deals with the plague. فَإِذَا سَمَعْتُمْ بِهِ بِأَرْضٍ فَلَا تَدْخُلُوا عَلَيْهِ وَإِذَا وَقَعَ بِأَرْضٍ وَأَنْتُمْ بِهَا فَلَا تَخْرُجُوا مِنْهَا فِرَارًا مِنْهُ. It says, if you come across a land where the plague has come down, then do not enter that land. And if the plague comes down onto your land and you are there, then do not leave your homes in the hope of escaping it. So it sort of makes a lot of sense. But here's quite an amusing part. It deals with epilepsy. And it says that the Greeks, or Galen, believed that epilepsy originated in the brain. So, however, they were ignorant. They didn't realize the true cause of epilepsy, which is the possession of the body by evil spirits. And it talks about the cure for epilepsy being exorcism.
Hardly scientific. But Islam's most tangible contribution to medicine is less in its specific remedies and more in its overarching philosophy. It is, after all, a religion whose central idea is that we should feel compassion for our fellow humans. And accompanied by Dr. Peter Porman, I'm going to see a physical bricks and mortar manifestation of medieval Islamic compassion. This is the Nur al-Din Hospital, the leading hospital of the Islamic Empire, built here in Damascus and now a museum.
This was built in the 1150s, 1154, I believe. One of the ideas which are stipulated in Islam is the idea to be charitable, and
yes,
charity,
zakah, yes.
Exactly, and an obligation to give alms and stuff like that.
Yeah.
And so, if you're a ruler or if you have a lot of money, what you could do is obviously
you could really be charitable,
and set up like a nice hospital like this one.
And within the hospital, Islam actively encouraged a high degree of religious tolerance, something we take for granted in modern secular society.
The hospital was open to all communities, so you would have Christians, you would have Jews, Muslims obviously, maybe other denominations, both as patients and also as practitioners. Like a Christian studies with a Muslim says, my best student was a Jew. And so the medicine which was practiced here transcended religion.
I mean, typically, how many physicians would there be?
Well, it depends. Well, like for certain hospitals, we hear figures of like 24 or 28 physicians. Yes, the physicians would do the rounds in the mornings, you see, do their prescriptions
that's the
and
sort
stuff
of thing
like that.
Yes, hasn't changed over the ages, yeah.
As a result of the translation movement, those physicians now became aware of the latest remedies from as far away as India and China. And as the new drugs filtered in from the rest of the world, hospitals started to set up a new kind of facility within their walls, the pharmacy.
So this notion of a pharmacy in a hospital, is that a new innovation?
Well, the whole package, certainly, that's new. And what is interesting, if you look for innovation, like on the level of pharmacy, if you look at Baghdad or even Damascus, it's at this crossroad of cultures. So loads of new things come in, like musk, for instance, myrobalan. You have like Indian drugs. There's like an Indian pill, for instance, which is good against headaches and to, bad breath, but also gives you sexual appetite and stuff like that. So
Cures your headache, gives you fresh breath.
Fresh breath. And gives you...
increase. And so it's like toothpaste, Viagra and aspirin.
That's right, all in one.
Fantastic.
Yeah. So, well, let's walk in here.
Peter wants to show me perhaps the most ghoulish aspect of Islamic medicine, surgery.
Here you have like a wonderful illustration. It appears that this is the first anatomical illustration in history. Like you see, it says adala, which means muscle. And so these are like the different muscles which move the eyelids.
So it was understood then that the muscles controlled the...
Oh, absolutely,
the lens in the eye.
Yeah, and moved the eyelid and stuff like that. So the other thing which we have here, which is really nice, is I think we have some, like ophthalmological instruments. For instance, it's a hook, could be used, for instance, like to kind of pull back your eyelid, that sort of thing. I mean, these instruments were very useful to the doctor.
Although these tools might look crude, eye surgery was one of Islamic medicine's great successes. One innovation was to improve an older technique for curing cataracts called couching, which in their hands had a success rate of over 60%.
In a living subject, the cornea would be clear and you'd be able to see the pupil clearly with the cataract sitting behind the pupil, the wide opacity.
To see how couching stands the test of time, I'm meeting up with eye surgeon Mr. Vic Sharma.
Right, the cataract is the lens inside the eye, which sits behind the pupil. As with time, with age, the lens gets cloudier and cloudier, and that's what is referred to as a cataract. Okay.
I've brought along a replica of a medieval couching knife and a description of the treatment by Al-Bukassis, which is the Latin name for the great 10th century Islamic surgeon Al-Zahrawi.
He says you take the couching needle in your right hand, if it be the left eye, and so on, and then thrust the needle firmly in, at the same time rotating it with your hand until it penetrates the white of the eye, and you feel the needle has reached something empty. So he's talking about how to dislodge.
Exactly.
So, I mean, maybe you can show me. We've got some eyes here.
Yep, and I'll certainly give it a shot, and what they would have done would have attempted to go in just by the white of the eye, just at the edge where the cornea is. And then what they are attempting to do is to sweep around, trying to break all those ligaments of that lens and trying to get the lens to drop away from the pupil to allow more light to enter in through the pupil and to brighten the subject's vision.
But of course you haven't got the capacity to focus.
Oh yeah, you haven't got a lens now, so that was a big problem until people started compensating that with specs later on.
Right. What is your feeling about how advanced and successful?
Well, they were on the general ballpark. They were at the right place. They were trying to remove the cataract away from the visual axis.
They understood the anatomy of the eye.
Exactly. They had some understanding of the anatomy of the eye, and that the lens was behind the pupil, and that's what was causing the visual loss. And so removing that, and that general principle is still the same.
Right.
And there are still accounts of it being used in certain parts of the world presently.
Looking back at medieval Islamic medicine with modern scientific eyes is frustrating. They take as true many things we know to be nonsense. But on the other hand, their desire to deal with this vast subject logically and systematically is admirable and truly marks a break with the past. One Islamic scholar, more than any other, embodies the synthesis of religion, faith and reason. His name was Ibn Sina, or Avicenna, as he's known in the West. He was a polymath who clearly thrived in intellectual and courtly circles. In 1025, he completed this, Al-Qanun fil Tib, or the Canon of Medicine. In it, Ibn Sina collated and expanded on all that had gone before him, medical ideas from Greece to India, and turn them into a single work.
So how would you place this book in a historical context?
Oh, it's hugely important. I mean, there are a few books which are as important as the canon, because what this encyclopedia does, it kind of, sweeps away everything else. It becomes a textbook. It supersedes a lot of other texts, and people even complain that, it's so good, it's so tightly organized, it's so easily accessible that, people forget to read the Greek sources in Arabic translations. This whole first book, this is the first book, contains what we call the kulliyat, the general principles. So it's all about how the human body works, how diseases work in general. The second book contains diseases, what we sometimes call from tip to toe, like from tip to toe. So he starts with the diseases of the head, and then he moves down, like the eyes, the ears, the nose, the mouth, and normally they end up at the sexual organs, you see.
At first sight, the sheer ambition of the 3 volumes is hugely impressive. Here's an attempt at diagnosis and cure for diseases as diverse as depression, meningitis and smallpox. And there's even detailed chapters on more common problems.
So, like for instance, here you have like headaches.
So different kinds of headaches.
في العلاج الصداع الحادث عن الروائح الطيبة. So headaches caused by pleasant, fragrant smells.
And then he's also got الحادث من الخمار, so hangovers.
Different kinds of you can get headache from sex.
Is that right?
Well, I mean, hasn't happened to me yet, but I mean, let's see. So, the treatment of headache caused by sex. ويجب لمن يعتريه ذلك عقب الجماع وبامتلاء أن يبدأ بالفast. So if somebody has or is befallen by, suffers from a headache after sex, and he also has a repletion, so he has too many superfluities or something like that, so يجب أن يبدأ بالفast. One has to first resort to venesection or bloodletting. ثم بالإسهال, and then you should use purging. In وجب كل واحد منهما. For both of them, I mean, like bloodletting and purging are necessary.
A lot of the stuff in here sounds like nonsense, of course, because this is not modern medicine.
No, it's not.
So how long was this taken seriously?
Well, the fundamental ideas contained here about how the body works, I mean, they haven't changed until the early 19th century. I mean, there was progress, obviously, on certain levels, but the essence was the same. And then came the big break with the discovery of bacteria and viruses and things like that. And from the second half of the 19th century onwards, medicine was totally revolutionized.
Ibn Sina's canon of medicine is a landmark in the history of the subject. Although much of the medical science it espouses we know now to be terribly misguided, its value lies in accumulating the best knowledge in the world at the time into one accessible, organized text. The canon would give future generations something to rewrite.
Cataloguing the world's medical knowledge has clear and obvious benefits. But the Islamic Empire's obsession to uncover the knowledge of the ancients went beyond practical matters like medicine. Many, like the Caliph al-Ma'mun, believed that the people of antiquity possessed dark, even magical powers. And what's more, new evidence is coming to light to show just how hard Islamic scientists worked to rediscover them.
To find out about that story, I have to visit the harsh, burnt yellow of the Sahara Desert in Egypt. There I am to meet an academic who wants to show me how the translation movement took the Arabs to Egypt on a quest to break a code, which they thought hid the secret of the dark art of alchemy. This is Saqqara, a necropolis or graveyard of the ancient pharaohs. Over a 10-acre site, it's a collection of burial chambers and step pyramids that were built in the 3rd millennium before Christ. These are said to be among the oldest stone buildings in the world.
Mind the step here?
Archaeologist Dr. Okasha Eldali is my guide. He was about to reveal the most astonishing story of my journey so far.
Oh, look at that.
Like most people, I believed that Egyptian hieroglyphs had remained completely undeciphered until the 19th century. Then came the chance discovery of the famous Rosetta Stone. This stone had the same inscription written in both hieroglyphs and Greek. It provided the crucial clues which British and French scholars used to decipher the writings of ancient Egypt. That's the usual story one hears. But Dr. Eldali has made a discovery that dramatically alters it. He has recently unearthed a number of rare works by the Islamic scholar Ibn Wahshiyya. What he did was figure out a correspondence between hieroglyphs like these and letters in the Arabic alphabet.
If you look here, for example, at Ibn Wahshiyya's manuscript, you see he's giving us the Egyptian hieroglyphic signs that have phonetic value
underneath.
Yes, and they have the phonetic value in Arabic underneath. So look very carefully at this one. He says "seen" underneath that seat.
Yes.
Now look at this seat here. That is S. That seat in Egyptian hieroglyphic is used for the sign S, "seen," which is what you see here, "seen." That is the name of the god Osiris. Osiris.
Oh, with an S.
That's the "seen."
Yeah.
This is the letter H. This one here.
This is the harp.
The water wave
Right.
is the letter N, or noon in Arabic. T, and the letter F.
These are all letters.
These are all letters. But then he realized...
But how did he decipher the hieroglyphs?
The one good thing about the early Arab scholars was their ability to link ancient Egyptian language, we call hieroglyphic, to link it with their own contemporary Coptic. They realized that Coptic is nothing but the later stage of ancient Egyptian language.
And they realized this because the translation movement had literally placed hundreds of Coptic texts into their hands. The scholars could now see a direct link between hieroglyphs and Arabic.
What fraction of these symbols would have been correctly deciphered?
They got about 14 letters. They cracked more than half of the Egyptian hieroglyphic correctly. So that was a remarkable achievement for people in the 9th century, 10th century.
Well, that's probably the biggest revelation for me so far on my travels, that Egyptology didn't begin in the 19th century. Yet again, it seems that Islamic scholars actually cracked hieroglyphics, and they cracked it for strange reasons. They cracked it because they were interested in astrology and alchemy. But here is another example of this amazing translation movement. They weren't just translating Greek and Indian and Persian texts, they were translating Egyptian hieroglyphics as well. Absolutely incredible.
Unfortunately for the Caliph al-Ma'mun, the hieroglyphs contained no alchemical secrets. But what this story reveals to me is the insatiable curiosity Islamic scholars had about the world. They were desperate to absorb knowledge from all cultures purely on merit, with no qualms about the places or religions from which it came.
Most intellectual traditions, including, if I may say so, our own, tend to work very hard to keep everybody else out. Whereas here we have an example of an enterprise which is desperate, curious, to turn itself into a net importer of intellectual product. And that's a very important lesson for the history of the sciences.
I was soon to see just how dramatically this fueled scientific innovation. But it's worth remembering that the translation movement wasn't just about science and medicine. As the capital Baghdad sat in the center of a vast, successful empire, it became home to an extraordinary flourishing of all kinds of culture. For this is the time described by 1001 Nights, of great and generous caliphs, magic carpets, great journeys, but also ambitious buildings, music, dance, storytellers, and the arts. Baghdad was such a cultured and vibrant city that one traveller of the time wrote, "There is none more learned than their scholars, more cogent than their theologians, more poetic than their poets, or more reckless than their rakes." It really must have felt like Baghdad and the Arabic Empire were the world leaders in civilization and culture. To be part of that city's growing intellectual elite must have been as exciting as it gets.
It was a new Muslim city. It only started to be built in 756. So it has that sort of sense of almost being on a frontier, of being something new, of being something different. It was full of courtiers, it was full of sort of nouveau riche individuals who were trying to make their way at the Abbasid court. And it is the sort of a place, if you like, where innovation is valued and appreciated.
At the heart of the city's intellectual life was a system called the Majlis. Now, the word Majlis could probably best be translated as salon or talking house. In 9th century Baghdad, what this meant was that the city's elite, the caliph, his courtiers, generals, and the aristocracy, would hold regular meetings, you might call them seminars or discussions, during which the city's cleverest men, the philosophers, theologians, astronomers, and logicians, would gather to discuss and debate their ideas.
It was not the case that people were expected to adhere to a particular line or adopt a particular religion. They were allowed to express their own sentiments and their own views very freely. The point was that they should do so in elegant Arabic and in good logical reasoning.
The effect of the Majlis was to create a heady mix of money and brains, with the best minds in the empire swapping ideas while simultaneously engaged in fierce competition for patronage.
It's at this point my investigation into the first wave of Islamic science returns me to the man we first met at the beginning of this story in the back streets of Cairo, the great mathematician who brought the West the decimal system.
Out of the very heart of this intellectual whirlwind came Al-Khwarizmi, mathematician, astronomer, courtier, and favorite of the Caliph al-Ma'mun. He was a product of his age, an immigrant from eastern Persia into Baghdad, surrounded by books, well-versed in learning from Greece, Persia, India, and China, and fearless in his thinking.
Al-Khwarizmi brought together two very different mathematical traditions and synthesized them into something new.
The capacity to have on your desk simultaneously two very different kinds of mathematics presses on models of what counts as calculation, what counts as measurement, and I think accelerates the process of intellectual change.
The first of these traditions came from the Greek-speaking world. Greek mathematics dealt mainly with geometry, the science of shapes like triangles, circles, and polygons, and how to calculate area and volume. The other great mathematical tradition Al-Khwarizmi inherited came from India. They'd invented the 10-symbol decimal system, which made calculating much simpler.
Thanks to the translation movement, Al-Khwarizmi was in the astonishingly lucky position of having access to both Greek and Indian mathematical traditions. He was able to combine geometrical intuition with arithmetic precision, Greek pictures and Indian symbols, inspiring a new form of mathematical thinking that today we call algebra.
As a physicist, I've spent much of my life doing algebra, and I can't overstate its importance in science. But it is a strange idea. I remember being perplexed when my math teacher first started talking about mathematics not using numbers, but with symbols like X and Y. It's an incredibly liberating idea because it allows you to solve problems without getting bogged down in messy numerical calculations.
So we have here this priceless manuscript, Kitab al-Khwarizmi's book, and
Professor Ian Stewart has studied algebra for much of his working life. Together, we looked at an early copy of the book in which the idea really took form.
I see here, although it's written sort of in the margin, the title of the book, Al-Jabr wal-Muqabala. So that's the first time the word Al-Jabr appears.
Algebra.
Algebra, that's where our word algebra comes from. Now, what I found very early on is that he said, I discovered that people require three kinds of numbers, judur wa amwal wa adad, so roots, squares and numbers. So what is he trying to do here?
This is what we would now call x and x squared. This is quadratic equations. This really is algebra. So he's setting you up for a book about how to solve equations by algebraic methods.
Okay, now quadratic equations I thought were around and being solved long before Khwarizmi, back to Babylonian times. So, what's the big deal about this book?
It's the point of view. He treats root and square as if they're objects in their own right. They're not just some number that we're trying to find out. They're a process you apply. What Al-Khwarizmi is thinking of is square means take the root and multiply by itself. And that recipe is true whatever the root might be. If it's 5, it's 5 times 5, it's 25. If it's 3, it's 3 times 3. He's giving you a general recipe, now called an algorithm, after him.
The algorithm comes from...
It comes from... It's another word that comes from Al-Khwarizmi, yes.
Now, he talks about this procedure here on the next page. You take the number multiplying the root, and then you halve it, and then you multiply it by itself. Then you add it to the other number and take the square root. That's the algorithm, is it?
That's right, and this is where you see the difference, because previous writers on the subject would have said things like, take half of 10, which is 5, square that, which is 25, and then they do another problem, take half of 12, which is 6, square that, which is 36, and they'd run you through this same process over and over again with different numbers, and it would be up to you to infer how to do it on the next problem.
But he doesn't do that.
He doesn't do that. He says, take half the root. Whatever the root is, take half the root. So half the root is actually an object. If the root is an object, half the root is an object.
So you don't have to have in your mind what that root stands for.
No, you can forget about what it stands for. When you come to square it, you just know, okay, I should square this thing. I don't care what the thing is. So you abandon temporarily this link with specific numbers, manipulate the new objects according to the rules that his book is explaining, and then the numbers that these objects represent in your particular problem will miraculously appear at the end, and you'll end up with x equals 3, or whatever it is.
So how revolutionary do you regard Al-Khwarizmi's work?
He made it possible for algebra to exist as a subject in its own right, rather than as a technique for finding numbers. The least interesting bit of an algebraic calculation is when you get to the end and discover that x equals 3. It's the route you take to get there. But if it was a special route for each problem and a different route for each problem, that wouldn't be interesting either. It would just be a big mess. There's this beautiful general series of principles, and if you understand those, then you really understand algebra.
what is the true global importance of algebra? It's been used throughout the ages to solve all sorts of problems. Let the mass of the cannonball be m. Let the distance it has to travel be d. Use algebra to work out the optimum angle you have to point your cannon. That sort of knowledge wins wars. Or let's call the speed of light c, the change in mass of an atomic nucleus m, and then calculate the energy released with the following algebraic formula: E equals mc squared. Mastery of that information truly is power. Algebra has helped create the modern world. Our science is unimaginable without it. It sums up so much that was remarkable about medieval Islamic science, taking ideas from Greece and India, combining and enhancing them. Similarly, modern medicine owes a considerable debt to the work of the Islamic physicians. But I think the real story of what happened to science in the Islamic world in the 8th and 9th centuries tells us more than any single discovery. What it really tells us is about the universal truth of science itself. I believe that the first great achievement of the medieval Islamic scientists was to prove that science isn't Islamic, or Hindu, or Hellenistic, or Jewish, Buddhist, or Christian. It cannot be claimed by any one culture. Before Islam, science was spread across the world. But the scholars of medieval Islam pieced together this giant scientific jigsaw by absorbing knowledge that had originated from far beyond their own empire's borders. This great synthesis produced not just new science, but showed for the first time that science as an enterprise transcends political borders and religious affiliations. It's a body of knowledge that benefits all humans. Now that's an idea that's as relevant and as inspiring as ever.
In the next episode, I investigate how one of the most important ideas in the world arose in the Islamic Empire. I discover how mathematics and experimentation fused together as the empire embraced a medieval industrial revolution. And in Cairo, I find out how these ideas led directly to today's world of science and technology.
Science and Islam continues next Monday night at 11:25. Tonight we're heading for Broadcasting House and a day out with U2.
Every now and then, an idea takes form that changes everything. It revolutionizes the way we see and understand the world around us. I believe that just such an idea took form in the medieval Islamic world. It's the idea that everything, from the stars above to the workings of our own bodies, is not arbitrary or whimsical, but subject to certain systematic rules. And what's more, that we humans can work out what those rules might be. And then we can refine and test our theories through observation and experiment. In other words, it's the idea we now call the scientific method.
For me, the story of the scientific renaissance that took place in the medieval Islamic world is a personal one. This is my cousin Samir's house in the Iranian capital, Tehran. I haven't seen some of the relatives on my father's side of the family in over 30 years. This is my not so tall but very beautiful Auntie Anisa. The Al-Khalili family is originally from the city of Najaf in Iraq, south of Baghdad. In fact, I grew up in Iraq. But when Saddam Hussein came to power, the family split. Many of the Al-Khalilis fled here to Iran. As my mother's English, I came to Britain with my parents. There, I pursued my passion for science, and am now a professor of physics at the University of Surrey. But now, I find that my own scientific work and my Arabic and Islamic heritage are intertwined. On my journey through the Middle East, I discovered that an astonishing leap in scientific knowledge took place here 1,000 years ago, under a powerful and flourishing Islamic empire.
Wealthy, powerful, successful cultures will produce enormous advances in understanding and in technique. And that's just what we find in Islam, in Baghdad, under a series of successful, powerful, wealthy, and self-confident Islamic regimes.
Over 1,000 years ago, the Islamic Empire was the largest in the world. It governed an estimated 60 million people. That was over 30% of the world's population. I found an archaeological fragment of this glorious past in a suburb of Tehran, not far from my cousin's house.
These ancient walls, tucked behind a back street on the outskirts of southern Tehran, are literally all that remain of the ancient city of Ray, the city that the great Persian geographer Al-Muqaddasi described as one of the glories of Islam. Of course, Ray was just one of a number of cities that flourished under early Islamic rule. From Baghdad, its capital, the empire spread across thousands of miles, from North Africa through to Central Asia. Cities like Al-Askar, Basra, Merv, Gurganj, Bukhara, each powerful and thriving cities. Each would have been rich in trade, alive with culture. Each would have had its own libraries, its own academies. These were powerhouses of the new science. This really was a golden age.
Think of that span of land. This is larger than any empire human civilization had ever known. Within that span of land, you can plug in the Roman Empire and it will fill just maybe, what, 1/3 of it, 1/2 of it, or something like that.
Reminders of this great Islamic empire are everywhere in the Arab world today. This football match in the Syrian capital Damascus is being played at the Abbasid Stadium. That's the name of the family who ruled the Islamic empire from 750 to 1258 AD. This large territory allowed them to raise enormous tax revenues to fund a search for knowledge and scholarship, which became known as the translation movement. They sent scholars around the known world to gather up great books and have them translated into Arabic. It's a legacy that's still alive in the minds of most modern Arabs.
قدموا يعني طوروا التقويم تقويم الشهر كمان وعربوا الكتب اليونانيه واهتموا بالعلم كثير بالطب وبالهندسه وكل
For medieval Islamic leaders, scientific knowledge was crucial to successfully running a vast empire.
They did have a big and sophisticated governmental administration, and obviously that needed knowledge. If you wanted to be an administrator and you had to assess taxes, you needed to know about mathematics. It also wants to be able to build monumental buildings. That requires the knowledge of architecture and, again, mathematical skills to construct fine buildings safely. Medicine, just to keep the elite happy and healthy. And those are the areas of knowledge which are first translated from other languages into Arabic.
The legacy of the medieval Islamic Empire is scattered across a vast region. There's architectural masterpieces like the Umayyad Mosque in Damascus, the Jama Mosque in Isfahan, and Al-Azhar University Mosque in Cairo. And then there are many ruins that still hint at past glories, like this, a crumbling 8th century palace deep in the Syrian desert. And this, a huge Muslim palace called Medinat al-Zahra, currently being excavated in southern Spain.
These are the impressive ruins of Medinat al-Zahra, the fantastic palace city built outside Cordoba in the 9th century by Abdurrahman III, who was the greatest of all the Andalusian caliphs. At the time that it was ruined, Cordoba was in fact the largest and most important city in Europe, a rival to Baghdad in the east for a center for Islamic scholarship and science.
And as I traveled, I saw how science, especially numerical record keeping and measurement, was crucial to dealing with the challenges of running a vast empire. This is the mighty River Nile as it flows through the Egyptian capital, Cairo. Since antiquity, its unpredictable floods have determined the fate of Egypt's people, bringing years of lean and plenty. By the 8th century, Cairo was part of the Islamic Empire, and the new rulers took the first step to understanding this mighty river in a scientific way. They built a device to measure it. Dr. Nader Al-Bizri of the Institute of Ismaili Studies is showing me the Nilometer. It's basically a huge colonnade that was built in a chamber connected by tunnels to the river. As the water rose or fell, its height could be read from the central column.
The central colonnade here is ultimately a measuring instrument. It is very precise. It's almost 1 inch between a marking and another.
Presumably they need to know seasonal variations in the height.
And to try to have some sort of record so that they could measure against certain years, where a year was known for a high level of flood versus another year known for its drought. Then they might perhaps take some precautions.
Yes.
The data collected from the Nilometer did have one practical use. By creating an objective record of the river's behavior, it allowed the rulers of the time to calculate how much tax to levy on Egypt's farmers. But whatever its uses, what I love about the Nilometer is how it shows that to understand the world, you have to build devices to measure it.
If you think very hard, it's never obvious that measurement can make sense of the world around us. The world appears, as a Western philosopher once put it, like a buzzing, blooming confusion. And the idea that we as a group have tools which are reliable, which have sufficient integrity, which have an intellectual grip that can make sense of the basic phenomena we see around us, that's an astonishing idea.
And one medieval Islamic ruler made measurement a personal obsession, giving it a scale and ambition that was truly unprecedented. His name was El-Ma'mun, and he became the caliph or ruler of the Islamic Empire in 813 AD. El-Ma'mun lived in a culture without portraiture, so all we have are later impressions of what he might have looked like. El-Ma'mun funded a range of scientific research, but one particular project was a personal favorite of his. And given that he ruled over such a large territory, it's hardly surprising what it was: map-making. In the second decade of the 9th century AD, El-Ma'mun commissioned a new map of the world, and his scientists did a pretty impressive job. It was a vast improvement on all maps that had come before. What we see here is that they've really got the Mediterranean, its shape and how it links in with the Black Sea, the Middle East, even the whole of Asia as far as China and Japan. They've even got the Indian Ocean and the east coast of Africa. It all looks pretty impressive for the known world at the time. Of course, what El-Ma'mun ultimately wanted to know was how much of the Earth as a whole did he possess? And this begged the question, just how big is the Earth?
It's a sign of amazing ambition that groups of scholars and craftsmen together can, as it were, capture the world. Where does that ambition and that confidence come from? Part of it comes from religious faith. Because the world was made by someone a bit like us, but much smarter, if we're smart enough, the thought was, we could probably make sense of a bit of what he did. And that's very clear as a motivation in a lot of Islamic, as in a lot of Christian science.
And more specifically, the practice of Islam demanded that its followers have a very clear idea of the size and shape of the world. Now, this is crucial information for Muslims because wherever they are in the world, they need to know the direction to Mecca for their prayer. This is known as Al-Qibla. Now, over such a large territory, finding the direction to Mecca is not a trivial problem. This problem was wonderfully illustrated when a mosque was built recently in Washington, D.C. Some worshippers were confused because the direction they were told to face when praying was slightly north and not southeast as they expected. After all, Mecca is southeast of Washington, and on a flat map, it does appear to lie in that direction. But on a curved sphere, the shortest distance between any 2 points follows what's called a great circle. So, for example, this great circle line between Washington and Mecca is quite different to what you might expect. So the direction to Mecca from Washington actually points slightly northeast rather than southeast. Of course, this is complicated stuff, but the key point for Islamic scholars is that knowing the direction to Mecca requires a knowledge of how steeply the Earth curves. And that means knowing how big it is. So El-Ma'mun commissioned his very best scientists to measure it.
Hello.
Hello.
Mr. Sami. I'm Jamal Khalili. Nice to meet you.
To understand how they did it, I'm meeting up with Professor Sami Chaloubi from Aleppo University in Syria, who's an expert in early Islamic science.
Come and join me.
عندما قسمها على 7.5 عندما قسمها على 7.5
Professor Chaloubi began by explaining the measuring technique, which El-Ma'mun's scientists first used and which they had inherited from the Greeks.
We're now talking about this, the earlier
Yes.
Aristophanes technique of measuring the circumference. It was repeated again by the Abbasid astronomers, was to measure the distance between 2 points and then look at the angle of inclination of the sun. So in Egypt, in Aswan down in the south, they regard the sun as being vertical. This is, near to the equator. And they worked out how far away from the vertical the sun was if they measured it from the north of Egypt in Alexandria, which is on the Mediterranean coast.
Al-Ma'mun's astronomers repeated the Greek experiment in Syria and Iraq by measuring the angle of the sun in the sky at noon at one known location. They then walked due north to a second location, carefully measuring the distance they travelled. At the second location, they once again measured the angle of the sun at noon. This angle would have been slightly smaller than the first one. With these figures, Al-Ma'mun's astronomers were able to estimate the Earth's circumference. They got a value of 24,000 miles, within 4% of the correct value. Not bad, you might think, but this method was flawed and ultimately unreliable. The main problem with it was that measuring the distance between two locations was incredibly difficult. It could only be done by the unreliable method of counting paces as you walked through the burning desert. A more reliable and sophisticated method for estimating the Earth's size was needed, and 2 centuries after Al-Ma'mun died, it came. What made it possible was a great leap of imagination, and the fact that by 900 AD, much of the world's mathematical knowledge had been translated into Arabic, so scholars could scrutinize and improve on it.
Out of this obsession with scholarly learning came a true mathematical visionary, Abu Rayhan Muhammad ibn Ahmed al-Bayruni. And like all Islamic scholars of the time, al-Bayruni was obsessed with the science and mathematics of the ancient Greeks, Babylonians, and Indians. And because of the success of the translation movement, he had literally on his desk the great work on geometry by Euclid, Ptolemy's Almagest, the Indian text, the Sinhind, and the famous work on algebra by Al-Khwarizmi.
Professor Chaloubi has brought along the book in which al-Bayruni describes how he combined algebra and geometry with some very simple and practical measurements to solve the epic problem of how to calculate the size of the Earth.
Bayruni, the text from
This is his
the
Mas'udi canon.
Yes.
This is Bayruni's canon, which I've been trying to get hold of, where he describes this fantastic experiment. And, oh, you found the page?
Yes.
Having read al-Bayruni's description of how to estimate the size of the world, I wanted to try it for myself.
First, he had to find a fairly high mountain from the top of which he could see a flat horizon. In this case, the sea.
What I love about this story is that with a few simple measurements around this small mountain peak, you can work out the size of the whole world. Al-Bayruni's first step was to work out the height of the mountain. He did this by going to 2 points at sea level, a known distance apart, and then measuring the angles from these points to the mountaintop.
So, to measure the angle to the mountaintop, Bayruni had to use a device like this called an astrolabe. It's basically a giant protractor. It has the angles in degrees marked around the outside and a pointer to help him determine his line of sight. So if we try now and determine the angle to the top, it has to hang freely, and then, okay, so if you let it hang.
I'd like to stress, if you haven't noticed already, that al-Bayruni would have made his measurements more meticulously than I am. He did them again and again to get consistently reliable results.
Okay, that's about it. And that is 24.5 degrees. Okay, so now we've determined one angle. We now have to go and pick our second spot along the beach.
The distance from the first to the second point must be measured accurately. In this case, it's 100 meters, and the 2 points must be in a straight line with the mountain. I measured the second angle to be about 26.5 degrees, and now had enough information to calculate the height of the mountain. Using trigonometry and algebra, Al-Biruni used a formula that relates the height of the mountain to what are known as the tangents of the angles he measured. Using my measurements, I get a figure for this mountain of about 530 meters. I now need only one more measurement to get the size of the Earth. And to get that, I have to climb to the top of the mountain.
What Biruni did next was measure the angle of the line of sight to the horizon as it dips below the horizontal. So we're going to try and reproduce that. So if you can lift it up so that it's hanging, and if I locate the horizon, okay, which is about ½ a degree, which is about the value that Biruni got. Now here's the really ingenious part. Biruni had measured 4 quantities, 3 angles and a distance. He used 2 of the angles and the distance to work out the height of the mountain.
Al-Biruni now had everything he needed. In essence, Al-Biruni imagined a huge right-angled triangle which has as its 3 corners the mountaintop, the horizon and the center of the Earth. Trigonometry told him that the angle he had measured and the height of the mountain are related to the radius of the Earth, and algebra allowed him to calculate it.
With this formula, Biruni is able to arrive at a value for the circumference of the Earth that's within 200 miles of the exact value we know it to be today, about 25,000 miles. That's to within an accuracy of less than 1%, a remarkable achievement for someone 1,000 years ago. For me, Biruni's experiment is an early dramatic example of a scientist using mathematical reasoning to extend humanity's reach. He really pushes the idea that abstract geometrical rules governing idealized shapes like perfect circles and triangles can help us to comprehend the real world. Einstein used precisely the same approach, admittedly with much more advanced mathematics, when he developed his general theory of relativity almost 1,000 years after Biruni. But both Einstein and Biruni were united by a single common idea. With mathematics, humanity can embrace the universe.
In this story of the birth of the scientific method, the Islamic scholar's ability to master sophisticated mathematics is the first crucial ingredient.
The second crucial ingredient is the use of experiments in science. Without experiment, theory remains meaningless and sterile. It's experimentation that allows theory to be held up against the real world. It gives it physical meaning. But whereas sophisticated mathematics grew out of the empire's obsession with the world's learning through the translation movement, practical experiments came from the daily needs of a powerful and expanding civilization.
The driving force of the expanding medieval Islamic empire was trade. It boomed from around 700 AD onwards, creating a massive demand for metal workers, glass blowers, tile makers, craftsmen of every possible kind. When this collided with scholarly tradition, symbolized by the translation movement, it had seismic consequences for science.
The sciences absolutely depend, astronomy is a wonderful example, chemistry is another, on really intense relationships between craft traditions of instrument making, of working with metal and fire, of working with medicines, drugs, plants, and scholarship, highly sophisticated literary and mathematical analysis. And the Islamic world is just such a place.
By around 800 AD, the great cities of the Islamic Empire dominated the world's trade. To its markets came silks, spices, drugs, fruit, perfumes and gold, from as far afield as India and China in the east and Spain in the west. Anything that could be traded was. A wonderful relic of this medieval trade boom are the great caravanserais, like this one in the Syrian capital, Damascus. This huge vaulted building was designed as a resting place for all the traders and their animals who visited the city. On their ground floors were wide spaces for animals and goods. And above, there were rooms for the rich merchants to refresh themselves before another day of haggling. One 10th century traveller talks of the riches and beauties of the bazaars, and that the income of the provinces and localities was between 700 and 800 million dinars. Markets like this in the Egyptian capital Cairo still capture the intensity of medieval trade. And still surviving in the modern world of the internet and the mobile phone is a fantastic example of how traders 1,000 years ago communicated across a vast empire.
So this is a carrier pigeon, its base is here, so wherever you took this pigeon all over Egypt, it will make its way back to this guy. There's a famous story that a rich Cairo merchant by the name of Anor wanted to grow cherry trees. So he sent a message with a carrier pigeon to a contact of his in Damascus asking for some seeds. His contact sent back 500 birds, each one carrying a small bag with seeds in it. The whole process took just 3 days. Sort of a medieval FedEx, really.
By 700 AD, the Islamic Empire was taking the first steps towards mass production. And in this world where knowledge of materials, metals, and how they're worked became increasingly important, one practice flourished. It's the practice that was inextricably linked with magic. Specifically, the dream to turn base metals into gold. The mysterious practice of alchemy.
The ancient art of alchemy was a mystical system of belief based on spells, symbols, and magic. But I believe it took Islamic scholars to turn this quasi-religion into something much more scientific. Chemistry.
Increasingly, the knowledge of the alchemists found more and more practical applications. For instance, when, during the last decade of the 7th century, the ruler of the Islamic Empire, Abd al-Malik, made the bold decision to create a common currency for all his dominions, he turned to alchemists for help.
The proportion of gold to other alloyed metals that you have to put into the dinar to make the dinar usable. Otherwise, pure gold will become very soft and you can't use it. So that proportion is adjusted by, believe it or not, in this period, the alchemists. It is the alchemists who knew how to combine metals together and how to get the proportions of this gold to silver and gold to bronze and so on.
I hunted down tangible evidence of the skill of medieval Islamic alchemists in the old markets in the Syrian capital, Damascus.
This is an Islamic dinar. The date of this is 128 after Hijri.
So the middle of the 8th century, almost 740s. This 1,300-year-old coin, made of an alloy of different metals, isn't just durable. It's also malleable enough to be inscribed with intricate Arabic writing.
No God instead of Allah.
Coin making is one of the many examples of how the practical needs of a booming economy began to turn the magical practice of alchemy into modern chemistry. What's striking about chemistry in the medieval Islamic world is the sheer quantity of manuscripts that deal with the subject. There are literally thousands that survive, dealing with subjects as varied as metallurgy, glass making, tile making, dyeing, perfumery, weaponry. There's even a description on how to distill alcohol. All this activity clearly points to a bustling economy, with consumers, soldiers, engineers, architects, all demanding innovation and all demanding new technology. A great example of applied chemistry in the medieval Islamic world was the manufacture of soap. This stuff, solid soap that you can really clean yourself with, was virtually unknown in Northern Europe until the 13th century, when it started being imported from Islamic Spain and North Africa. By that time, the manufacture of soap in the Islamic world had become virtually industrialized. The town of Fez boasted some 27 different soap makers. And cities like Nablus, Damascus, and of course Aleppo became world-renowned for the quality of their soaps. A 12th century document has the world's first detailed description of how to make soap. It mentions a key ingredient, and it's a substance that became crucial to modern chemistry, an alkali. Now, alkaline substances are crucial to soap making. But what's interesting is that our word alkali derives from the Arabic al-qali, which means ashes. That's because back then, alkalis were manufactured from the ashes of the roots of certain plants like saltwort. Islamic chemists' new understanding of alkalis and other new chemicals gave another industry a lift too, glass making. The Islamic chemists discovered that they could change the color of glass using newly discovered chemicals like manganese salts. And they built industrial furnaces, some several stories high, to manufacture glass in huge quantities. The legacy of their skills can still be seen in beautiful stained glass windows. Islamic chemists also developed many other colors, pigments and dyes, using their new alkalis and metals like lead and tin. These helped architects to decorate mosques like this one in the Iranian city of Isfahan in a glorious range of colors and designs. Chemistry was also driven by the booming market in perfumes. In the main market in Damascus, traders still make up your favorite scent, as they would have 1,000 years ago. So it basically has a base of alcohol, and then he adds to it the oils from the plants that you want. Jasmine and rose water and mint, but these days they'll use. Very nice. Yeah, I think I'll buy some of that. Perfumiers pushed chemists to come up with ever more ingenious techniques for extracting subtle and fragile fragrances from flowers and plants. They responded by refining and really establishing a technique that all chemists would instantly recognize today: distillation.
Many of the techniques originate with Islamic scholars or even earlier.
Dr. Andrea Sella, a chemist from University College London, shows me how distillation was used.
Distillations would have been done in devices sort of related to these. This is what's now called a retort, and we don't really use them anymore, but retort comes from the word to bend. In other words, a flask which has been bent over, and that's crucial. Well, many of the techniques...
The shape means that a gas produced in the flask is forced to condense in the spout, and it's the main way of extracting scents from flowers and plants.
Now, the idea here is that you heat at this end and you collect at the other. And so we should actually take a look and see if we can do a quick distillation with rose petals. First, we need to just put in a little bit of water. The water and steam will essentially control the temperature. What we don't want is for this to get too hot.
The trick with this kind of distillation is to use heat to release the scent molecules, but at the same time making sure that these delicate substances aren't destroyed in the process.
You actually use the steam to control the temperature, and the steam will carry those smells over. You can see the liquid coming up, condensing in the long tube. And there is already liquid coming over.
Through, yeah.
And that should be carrying with it some of the sort of rose water smell.
Yes, you can really smell it.
This picture shows a 14th century perfume distillery. Middle Eastern perfumes were known to have been sold as far away as India and China. The Islamic chemists also played a pivotal role in another more gruesome industry, weaponry. Historical records during the Crusades talk in terrified tones of how the Muslims would attack the Christians with burning missiles and grenades, striking fear into the hearts of the defenders. Many of these use a substance known as Greek fire. Islamic chemists improved on Greek fire by using and refining a naturally occurring resource, petroleum. They developed the idea of distilling petroleum, or naft, to create a lighter, extremely flammable oil, which they mixed with other volatile chemicals to make them burn furiously. And the result was clearly terrifying. What all these medieval Islamic texts on chemistry have in common is their great attention to detail, which is clearly based on careful experimentation. In fact, the whole idea of a laboratory where chemical and industrial processes can be tried out really takes hold at this time. The ingenuity of medieval Islamic chemists is impressive. But I wanted to know something deeper. What contribution did they make to our modern understanding of the principles behind chemistry? This is the centerpiece of modern chemistry, the periodic table. It lists all the known elements. Its key idea is to group substances with similar properties together. On the far right, for instance, are the inert gases. On the far left are the volatile metals. The periodic table is a triumph of classification, giving scientists a way of organizing their knowledge of the material world.
Classification is simply a way to think clearly. I mean, what you need when you have some ideas about how the world works is that gives you a kind of schema, and you chop the world up into categories. And that actually helps you to understand, to make sense of what's around you.
People had been trying to classify the material world since ancient times. The Greeks, for instance, thought there were just 4 worldly elements: air, earth, fire, and water. But this idea was a philosophical one and had little practical value. And that's what medieval Islamic chemists really changed. They used experimental observations to classify the stuff the world is made of. At the forefront of this was a medieval Islamic doctor and chemist called Ibn Zakaria al-Razi, who was born here in the city of Ray, just outside the Iranian capital Tehran, in 865 AD. Al-Razi's classification was very different from the Greek one. He argued, for instance, that minerals, roughly stuff we dig out of the ground, should be classified into 6 groups, depending on their observed chemical properties. The same guiding principle that lies behind the modern periodic table.
Now, what I've done is I've brought materials from his classification scheme. And we have here what he called the spirits. We have the metallic bodies, we have the stones, then we have the atriments, the salts, and finally the boraxes.
Each of Al-Razi's groups had a profoundly different experimental behavior. For instance, spirits were flammable. The metals were shiny and malleable. Salts dissolved in water. Of course, these classifications are not the way we do it today. But the point is that for the first time, Al-Razi was grouping substances on the basis of experimental observations, not philosophical musings.
We've come over 1,000 years since the work of Al-Razi. What sort of debt does modern chemistry owe to him for his classification?
Well, I think with Razi we start to see that the first classification which really leads on to further experiments, the first schema which allows people to start doing rational work. And so really he lies at the start of almost formal chemistry, which ultimately leads to our periodic table.
I believe that what we see in the work of the Islamic chemists and alchemists is the first tentative steps to a new science. Yes, by our standards, it contained a lot of magic and mumbo-jumbo, but it placed an emphasis on experimentation that was truly revolutionary.
But bigger and better was to come, because Islamic mathematics and the experimental techniques of Jabir ibn Hayyan and Al-Razi were about to be welded together in a completely innovative way that would revolutionize their work and create the modern scientific age.
Until the 9th or 10th centuries, ideas about science and how the natural world worked were dominated by the Greek philosopher Aristotle, and they were very different from ours today. He believed that mathematics was concerned only with an abstract world of perfect forms, of idealized shapes like circles, squares, and triangles. It had no power to explain what we observe in the world around us, a world characterized by irregular, wonky shapes and constant change.
Physics is a Greek word meaning the science of change. And for the classical Greek tradition, there was a strong sense in which the science of change was in contradiction with mathematics. Mathematics dealt with perfect knowledge, with the unchanging world of mathematical forms. And it seemed in principle extremely unlikely that processes of coming into being and passing away, of growth and of decay, of qualitative change, could be captured with the beauties of geometry and mathematics.
The story of how humanity shook off this idea and began to see that mathematics is actually an incredibly powerful way of describing the world around us is long and complicated. But for me, Islamic scientists played a crucial role, and I believe one man really led this movement to turn mathematics from a language of abstract thought into a truly practical science. He was, like me, from Iraq, and his name was Ibn al-Haytham.
What al-Haytham and his contemporaries argued for was the possibility, in a way, of a single science, which would be both mathematical and philosophical, which would link together a physics, a science of change, with a mathematics, a science of quantity. And that seems to me to be radical and crucial for the construction of new forms of reliable knowledge.
Ibn al-Haytham was born in 965 AD in the southern Iraqi town of Basra, and other scholars regarded him as a prodigy.
He shot to scientific fame just after the turn of the first millennium and was an incredibly innovative and brilliant scholar. His reputation as an intellect spread throughout the empire. But it was this reputation that would almost cause him to lose everything when he took up the poisoned chalice of trying to tame one of the world's greatest rivers. There's a wonderful, if suspiciously apocryphal story about how Ibn al-Haytham's career as a scientist was transformed. It concerns the Nile and how, just after the turn of the millennium, Ibn al-Haytham was asked by the ruler of Egypt to find a way of controlling it. Could he prevent its unpredictable and potentially devastating floods and droughts? But it didn't take Ibn al-Haytham long to realize that the Nile was way too large to control. On hearing this, the Caliph flew into a terrible rage and ordered Ibn al-Haytham's execution. Ibn al-Haytham responded by feigning madness. The execution was called off and he was placed under house arrest. There, with time on his hands to contemplate, the story goes, Ibn al-Haytham considered deep and fundamental questions in physics. And he began with a truly enigmatic and universal problem. He asked if the wonderful and entirely mysterious nature of light and vision could be explained by mathematics and geometry. Under house arrest, or perhaps here in the rooms of Al-Azhar University in Cairo, Ibn al-Haytham carried out a series of experiments that created the modern science of optics. I'm with Dr. Al-Bizri, who has carefully studied Ibn al-Haytham's work. He explained that Ibn al-Haytham first considered the Aristotelian explanation for how we see, an explanation that was completely unmathematical. Aristotle argued that when we look at, say, a tree, its essence or form emanates from it and then mysteriously flows into our eyes.
So if I'm, for instance, now looking at the buildings and the trees on the banks of the Nile, I'm receiving the forms of these buildings and these trees in the eye, abstracted from their matter.
According to Dr. Al-Bizri, Ibn al-Haytham found this idea deeply unsatisfactory. He wanted a mathematical explanation. And looking back at existing Greek writings, he found one, although it was obscure and bizarre. This idea claimed that we see because light rays come out of the eye.
Ultimately, it says that vision occurs by way of the emission from the eye of light that is shaped in the form of a pyramid or a cone.
This cone-shaped beam illuminates what we're looking at and is defined by nice geometric straight lines. It seems Ibn al-Haytham liked this mathematical approach, but immediately spotted its flaws. If we see, he asked, because light comes out of the eye, why does it hurt when you look at a bright object like the sun, but not hurt when you look at something dim? Or at night, can light from our eyes really be lighting up distant objects in the sky? So, in an inspired piece of thinking, Ibn al-Haytham combined the two Greek ideas and defined our modern understanding of light and vision. Light, he said, does travel in straight lines that obey geometric laws, but instead of them coming out of the eye, these rays travel into it.
It is the development of an entirely new theory, and also methodologically, it is the beginnings of mathematizing physics.
What Ibn al-Haytham did was take the principles of geometry with its rules governing straight lines and apply them to the real world. He then designed experiments which would test whether the real world measured up to his mathematics. In about 1020, Ibn al-Haytham published his groundbreaking geometric explanation of light in his Kitab al-Manadhir, or Book of Optics.
And what really marks this book out as science is that Ibn al-Haytham carefully justifies his theories with detailed experiments that others can repeat and verify. He starts from first principles to find out how light travels. For his first experiment, Ibn al-Haytham wanted to test the idea that light travels in straight lines. Now, to do this, he took a straight tube on which he'd drawn a straight line down the side and a ruler, again with a straight line down the length of it. And by matching the two together, he was convinced then that the tube was straight. Now, if he uses it to look at an object, in this case a candle, he can see the candle through the tube, which is good evidence that the light is travelling up in a straight line. But just to be sure, he then blocked the end of the tube. And then, by looking at the candle again, of course, he can't see it, because what this does is confirm that the light doesn't travel to his eye via any other route in a curved path outside the tube, proof that light only travels in a straight line. Now, this might sound quite trivial and obvious to us, but Ibn al-Haytham was starting from first principles. Then, through experiment, he extends his light travels in straight lines idea to many other phenomena. He explains how mirrors work by arguing that the angle the ray comes in at is the same as the angle it bounces off at. He explains what we now call refraction, why objects look kinked in a glass of water, arguing that light rays bend when they move from one medium to another. And then he tackles the nature of vision. Ibn al-Haytham wanted to understand how an object makes an image on the retina of the eye. So he built what he believed was a stripped-down version of the eye, which is basically a black box with a tiny hole in it. This is what we call today the camera obscura. He next took his subject, in this case Anna, who's very brightly lit, and we now go inside the box to see what the image looks like. Now that I'm inside the camera obscura and I've allowed my eyes to get used to the dark, we can open the hole. And there we clearly see the image of Anna waving on the screen. But the image is inverted because light travels in straight lines, and so the light from her head has to move diagonally downwards to hit the bottom of the screen, and light from her feet travels diagonally upwards to hit the top. But more importantly, what this proved to Ibn al-Haytham is that there's a one-to-one correspondence between every point on the object, on Anna, and every point on her image on the screen. Just like a modern scientific paper, the attention to detail in the Kitab al-Manadhir is incredible. His book isn't just a dry scientific treatise, it's a manual for future generations. In his work, he constantly justifies his theories about light with experimental observation. And he describes his experiments in great detail so that other people can repeat them and confirm his ideas. His message is, don't take my word for it, see for yourself. I believe that Ibn al-Haytham was one of the very first people to ever work like this. This, for me, is the moment that science itself is summoned into existence and becomes a discipline in its own right. What I find so impressive about Ibn al-Haytham is how once he arrives at his mathematical theories, he then uses them to extend our knowledge of the real world. So, for instance, he used his new ideas about light to deduce that the Earth's atmosphere is of a finite thickness, and he even estimated what that thickness is. He did it basically by measuring how long twilight lasts. He rightly assumed that the reason it continues to be light after the sun has dropped below the horizon must be because its rays bend as they enter the Earth's atmosphere. The length of twilight and an educated guess for what we today call the air's refractive index gave Ibn al-Haytham a way of estimating the thickness of the Earth's atmosphere. He came up with a figure of around 40 kilometers, about half of the modern value. That's pretty impressive. It really shows how mathematics extends the power of science to explain. On my journey so far, I've been overwhelmed by the sheer intellectual ambition of medieval Islamic scientists. When their leaders asked them to find out the size of the world, scholars like al-Biruni used mathematics in startling new ways to reach out and describe the universe. And as trade and commerce boomed, scientists like al-Razi responded by developing a new kind of experimental science, chemistry. But if there's one Islamic scientist we should remember above all others, it is, in my view, Ibn al-Haytham, for doing so much to create what we now call the scientific method.
The scientific method is, I believe, the single most important idea the human race has ever come up with. There is no other strategy that tells us how to find out how the universe works and what our place in it is. Of course, it's also delivered technologies that have transformed our lives. So the next time you jet off on holiday, or use a mobile phone, or get vaccinated against a deadly disease, remember Ibn al-Haytham, Ibn Sina, al-Biruni, and countless other Islamic scholars 1,000 years ago who struggled to make sense of the universe using crude mirrors and astrolabes. They didn't get all the right answers, but they did teach us how to ask the right questions.
In the next episode, I travel to Syria and northern Iran to find out about the great Islamic scientists who revolutionized astronomy, making it a truly modern science. And I'll also discover how the man many consider to be the father of the European scientific renaissance, Copernicus, borrowed from Islamic astronomical theories. And I'll unravel the mystery of how the golden age of Islamic science came to an end.
And there's more from Science and Islam next week. Next tonight, plunging right into the thick of it with more biting comedy.
The sun, the moon, the planets and stars have always fired our imaginations and fueled our mythologies. And studying the heavens, astronomy, is surely the oldest scientific discipline there is.
What's really unexpected, I guess, is that astronomy has repaid our interest in it over the centuries. Time after time, it's been the place where new ideas have emerged, and it's often led the rest of the sciences.
I'm a professor of physics at the University of Surrey, and the ideas and theories of the great European scientists like Galileo, Newton and Einstein lie at the heart of my work. But there's another side to me. I'm half Iraqi, and I'm keen to investigate stories I'd heard as a schoolboy in Baghdad of great astronomers from the medieval Islamic world whose work shaped the discoveries of these later Western scientists. So I'm going on a journey through Syria and Egypt to the remote mountains in northern Iran to discover how the work of these Islamic astronomers had dramatic and far-reaching consequences. There, I'll discover how they were the first to attack seemingly unshakable Greek ideas about how the heavenly bodies move around the earth.
It was Islam that paved the way for one of the greatest upheavals in the history of science.
This is the University of Padua in northern Italy. I'm here to see incontrovertible evidence that one of the greatest breakthroughs in European science links back to the earlier work by Islamic scholars.
Because it was a news one that at that time...
Astronomer Dr. Luisa Pigiotti and I are climbing up to the 18th century observatory. At the top, she promises to show me one of the most important books in scientific history. So, what do we have here?
Okay, this is the second edition of the Revolutionibus.
Copernicus.
Yes.
This is De Revolutionibus Orbium Celestium, which was published in 1543 by the Polish astronomer Nicholas Copernicus.
Is it the second edition?
The significance of this book is enormous. In it, Copernicus argues for the first time since Greek antiquity that all the planets, including the Earth, go around the Sun. For thousands of years, everyone had believed a very different view, that the Earth is static and everything, including the stars, sun and planets, move around it.
And here there are all his system, okay?
Oh, there we go.
And the system.
The sun
okay.
in the
It's
middle.
a famous drawing,
Yes.
this one.
Oh yes, and there's Terra.
With the moon.
With the moon
with
going
the moon,
around it.
Okay, yes.
This is an astonishing book, and many historians credit it with starting the European scientific revolution.
There are the principle.
The first crucial step in a journey that led to modern physics.
Is another eruption of the Earth.
Well, I agree. But it does seem a bit odd that one doesn't hear much about where Copernicus got his ideas and information. The impression is that they came out of nowhere.
The beginning?
And the beginning is all in Arabic. It certainly is a real revelation to me that he explicitly mentions a 9th century Muslim for providing him with a great deal of observational data, an astronomer who lived in Damascus called al-Battani. Like all the great scientists of the Islamic Empire, al-Battani lived in a culture without portraiture. All we have are later impressions of what he might have looked like.
And here he mentioned Hipparchus, Calippo, Ptolemy, and so on, and he started to mention what he called Macometus Aratensis, and means Al-Battani.
Okay. And then the second book here.
And the second book is, we can look at the beginning in Latin.
I see, we can open it. Copernicus, in fact, made extensive use of al-Battani's observations of the positions of planets, the sun, the moon, and stars. He worked with Latin translations, similar to this one, of the Syrian astronomers' data. Kitab al-Zij al-Sabi. So this is Battani's Zij, his book of star charts. So it has the Arabic...
Yes, all the Arabic
on one side,
treatise, yes, and then the Latin version.
That's convenient.
But he had the data, the observational data by Al-Battani. You know,
and Copernicus's book is full of clues that hint at other past sources. And though al-Battani is the only Islamic astronomer Copernicus actually names, recent detective work has uncovered clues that Copernicus based many of his ideas on the work of other Islamic scholars. The clearest example is Copernicus's use of a mathematical idea devised by the 13th century Islamic astronomer al-Tusi, called the Tusi couple. Back in England, I compared a copy of al-Tusi's Tadhkira fi Ilm al-Hay'a with another edition of Copernicus's Revolutionibus. In it, there's a diagram of the Tusi couple, and there's an almost identical diagram in Copernicus's book, even down to the letters that mark the points on the circles. So in al-Tusi, there's the Arabic alif, which is A, there's the ba, which is B, the Jim over here is the G, and the dial at the center, D. It's a remarkable similarity. Now, this might just be coincidence, but it's pretty compelling evidence. In fact, I truly believe that Copernicus must have been aware of Al-Tusi's work and other Islamic astronomers. Further detective work also shows that Copernicus used mathematical ideas for planetary motion that are remarkably similar to ones developed by another Islamic astronomer, a 14th century Syrian called Ibn Shatir. For some historians, this cannot be coincidence.
Copernicus, to me, I have no proof. I don't have a smoking gun. But to me, it looked like, and again, by analyzing his own works, it looks like he was working from diagrams. Somebody gave him a geometric diagram of what was done by Ibn Shatir to solve the problem of the moon, for example, to solve the problem of the upper planets, to solve the problem of the movement of Mercury. He had diagrams, and he was genius enough to be able to figure out from the diagrams what was the underlying theory behind those diagrams.
So, far from emerging from nowhere, it seems Copernicus's work will be better described as the culmination of the preceding 500 years of Islamic astronomy. I wanted to investigate this story, find out more about those astronomers and their ideas. But before that, I wanted to investigate an even deeper question. What actually motivated medieval Islamic scholars' interest in astronomy? This is the Umayyad Mosque in the heart of the Syrian capital, Damascus, and is one of the oldest in the world. And I'm here on a kind of treasure hunt.
Well, it says in the books that there is a sundial on the top of the Arus minaret, the bride minaret over there. So we'll see whether it is there or not. So
this is Dr. Reem Turkmani, an astrophysicist and medieval astronomy expert from Imperial College London. And we're looking for one of the most accurate sundials made in the medieval world. And equally exciting for me is the fact that it was made by one of the Islamic astronomers who had so heavily influenced Copernicus, Ibn Shatir.
Let's see.
Officials in the mosque claim that the sundial was removed in the 19th century, but Reem's research suggests that an exact replica might still exist, high in one of the minarets, hidden from view. It's not quite the lost Ark of the Covenant, but the idea of discovering a 150-year-old artifact is still quite something. Would you recognise anything if you had a look?
I need to look at the other window, sorry. No.
No, it is further up.
Yeah.
Marking time accurately is essential to Islam. The Quran requires the faithful to pray 5 times a day at 5 very precise times. At the exact moment of dawn, when the sun is overhead, in the afternoon, at sunset, and then again at the moment of nightfall. So for early Islam, an accurate sundial was an extremely important fixture in many mosques.
That's it, I found it. I found it.
Yet,
So here it is,
right.
That's it, look. Just as described in the book.
It's hidden by the pillar.
Yeah, no wonder they didn't know that it exists here.
We've
It's
got an
all
owl mosque.
covered with the pigeons filth.
Pigeon crap.
Yeah.
Oh,
Oh, great, thank you.
try that.
So, let's see. So, now, this consists of 3 sundials. The main big one, and there's the northern one and the southern one. There is a line here for Salat al-Dhuhr, the midday prayer, and there is one for the afternoon prayer.
Ibn Shatir had calculated the arrangement of these lines so that the sundial remains accurate all through the year, even though the length of the days change.
They will have the timekeeper. It's a very important job.
So he would sit here watching the shadow,
exactly.
And exactly the precise moment for prayer, he'd signal to the muezzin to start the call for prayer.
Exactly.
Okay.
Ibn Shatir's sundial, accurate to within minutes, really showed me how Islam required its scholars to make meticulously accurate observations of heavenly bodies. And I began to understand why Copernicus was so impressed by the work of his Islamic predecessors. They really brought standards of accuracy and precision to astronomy that were unheard of before. They'd calculated the size of the Earth to within 1% and created trigonometric tables accurate to 3 decimal places. And when I met up with Reem Turkmani again on Mount Qasyun outside Damascus, I was to hear about the Islamic astronomer who personified accurate observation, the man whose astronomical tables and measurements Copernicus explicitly makes reference to, Al-Battani. Born in 858 in southern Turkey, Al-Battani made accurate astronomical measurement a personal obsession.
The story goes is that Al-Battani used to observe on this mountain here and in this observatory.
Over 40 years, from 877, both here and in the town of Raqqa, Al-Battani's great project was to work out as accurately as possible the length of the year.
This is a copy of the original manuscript.
Okay.
So I'll show you the chapter at which he explained the length of the year. Okay? The chapter 27. So he first started here by citing the ancient values of the Egyptians and the Babylonians, right? And he gives the length of year.
Their estimate of the year was 365 days, 6 hours, and just over 10 minutes. To improve on this, Al-Battani used his ingenuity and a device like this, an armillary sphere. He used it to measure how the length of shadows varied over the course of a year. With this information, he was able to work out the precise day on which it's both light and dark for exactly the same time, the so-called equinox. And he repeated his measurements over the course of 40 years. Now, here's the clever bit. He examined a Greek text that was written 700 years earlier and discovered the precise day on which its author had also measured the equinox. He now had 2 vital pieces of data: the number of days between the 2 observations and the number of years. He divided the first number by the second to arrive at an astonishing result. A year is 365 days, 5 hours, 46 minutes, and 24 seconds.
And he gets the new number, which was only 2 minutes of the modern observations.
2 minutes.
2 minutes
so
of only.
The length of a year to an accuracy of just 2 minutes.
Exactly, the one he calculated.
What's astonishing about the accuracy of Al-Battani's measurements is that he had no telescope. He used an armillary arm, his naked eye, and devices like this, an astrolabe.
So you move the pointer and you move this disc with it to point towards the North Star. Then these small pointers here, they will give you the location of the rest of the stars and the planets. Yeah.
Despite this, among his many other observations is an incredibly accurate figure for the Earth's tilt of just under 24 degrees, about half a degree from the figure we now know it to be. And he didn't stop there.
He measured variations in the diameter of the sun to such accuracy that it led him to an astonishing conclusion. This distance, the furthest point the sun reaches from the Earth during the year, known as the apogee, actually changes from one year to another. Also, his tables showing the position of the sun and the moon, which is what Copernicus refers to some 600 years later, set a new standard in precision and accuracy. So al-Battani and his fellow Islamic astronomers were clearly good observers. But so what, you might ask? Well, the answer is that their observations began to suggest to them that the prevailing Greek theory that described how everything in the heavens revolved around the Earth had some serious flaws. This Greek tradition, which had been unquestioned for over 700 years, was based primarily on the work of one of the greatest astronomers of the ancient world. Claudius Ptolemaeus, or Ptolemy, was a Greek astronomer based in Alexandria in the 2nd century AD. He wrote one of the greatest texts in astronomy, the Almagest, which was basically a distillation of all Greek knowledge on the celestial world. Ptolemy believed that the sun, the moon, the planets and the stars all sat on crystal spheres that rotated around the Earth. So the moon sits on the innermost sphere, followed by the sun and the planets, and finally a patchwork of stars on the outermost sphere. So we human beings sit at the very center of the universe, with the rest of the universe rotating around us. But as Ptolemy himself realized, there's a problem with trying to describe the heavens as a place of mathematically idealized perfect spheres. And that is that the planets don't really play ball. As they move across the night sky, they change speed, appear to get bigger and smaller, and even go back on themselves. Ptolemy tried to explain this away by arguing that the planets sat on small spheres called epicycles, which rotated around a bigger sphere called a deferent. This explained why they might look as though they were changing size, and why they sometimes even change direction. Unfortunately, that still didn't fit all the facts. It didn't easily explain why the planets appear to speed up and slow down. So, rather desperately, Ptolemy fudged his model further by moving the Earth away from the center of the deferent and having the deferent rotate around an arbitrary point in space, the equant. But now, the works of astronomers like al-Battani started to strain Ptolemy's ideas to breaking point. Their careful observations began to suggest that even with Ptolemy's unwieldy equants and deferents, the actual behavior of the heavens didn't fit the data.
So what do you do if you were an astronomer living in Baghdad and you have all those results on your table? The very first requirement is to say, this Greek tradition is not as trustworthy as it is advertised to be. And now, of course, they begin to say, if the fundamental values of the astronomical tradition of the Greeks, which we could double check and we found them to be in error, what else is in error? They began to question now the more basic foundational astronomical, cosmological foundations of the Greek tradition.
And question they did. What's absolutely striking about the writings of Islamic scholars by the 9th century is the increasing use of the word shukuk, which in English means doubts.
They showed that it's sometimes necessary to doubt an idea that everyone around you believes unquestioningly. Islamic doubting of Greek astronomy began the slow process of undermining the notion that the Earth is at the center of the universe. To doubt takes great courage and imagination. But if the great dialogue between Islamic and European astronomers shows anything, it's that doubt, or shukuk, is the engine that drives science forward. One of the first great shukuk scientists was called Ibn al-Haytham.
He was born in the Iraqi city of Basra in 965 AD and was among the first to argue passionately that scientific ideas are only valid if they're mathematically consistent and reflect reality. And when he applied his fierce, rigorous intelligence to Greek astronomy, he immediately spotted that there was a fundamental contradiction at its heart. On the one hand, Greek cosmology argued that everything in the heavens revolves around the Earth. On the other hand, Ptolemy, in his Almagest, argued that if you want to mathematically predict how the sun and planets move, you have to pretend that they go around an arbitrary point in space, the so-called equant. This is clearly a contradiction. The heavens can't both go around the Earth and not go around it at the same time. Ibn al-Haytham hated this nonsensical contradiction. In the early 11th century, he wrote a paper, Al-Shukuk ala Ptolemaios, or Doubts on Ptolemy. In it, he writes with barely contained frustration, Ptolemy assumes an arrangement that cannot exist.
Ibn al-Haytham says that is a total absurdity. We cannot accept that, and furthermore, he says, it's not a slip of a tongue. Ptolemy knew that it was an absurdity, and he shows us where Ptolemy himself was embarrassed by having to introduce it. So he says there is a fundamental reasoning problem, meaning that the Greeks knew that Ptolemy knew that he was making a mistake, but he knew he couldn't do any better, and hence now the challenge is to do one notch better, and hence to be able to fix this. That, in my explanation, begins to be the program of research for all astronomers to come.
In order to achieve that project, you had to be convinced that it was possible to make high precision mathematical models of the way in which planets and stars move that would really capture how they are in the heavens.
Ibn al-Haytham, in effect, laid down the challenge for all astronomers who followed, which was to come up with an explanation for how the heavens move that is both mathematically consistent and agrees with what we observe. The final answer to this would come from faraway Europe with Copernicus and others, but the next and crucial breakthrough came somewhat closer. The top of this mountain in northern Iran was the adopted home of the man who was the next of Copernicus's Islamic influences, Nasr ad-Din al-Tusi. He would succeed in rewriting Ptolemy's theory, which would ultimately lead to the overthrow of the geocentric view of the universe, and so the birth of the modern scientific age. This is the remote castle of Alamut, al-Tusi's adopted home. For many years, it was the home of a Muslim sect called the Ismailis.
It's a lovely secluded spot, and it was the center of the Ismaili movement. It's not surprising that al-Tusi would find a home here. And it wasn't just him. Many other scholars were gathered here, and there seems to have been a library. It was a center for learning as well as a military stronghold.
Here, this is the main gate, northern gate of the upper castle of Hassan Sabba.
A new archaeological dig is now revealing under the castle, hewn into the living rock, a warren of rooms and studies, a mosque and living quarters for this extraordinary community of soldiers and scientists.
This is the court of mosque or center of headquarters of castle.
And it was within these cramped conditions that Al-Tusi started his masterwork of the shukuk, or the doubts, the tadhkirah. In it, he finds an answer to Ibn al-Haytham's first challenge: how to eliminate Ptolemy's equant. Instead of a sphere rotating around an arbitrary point in space, Al-Tusi devised a series of two nested circles which rotate around each other in such a way that they eliminate the equant. The nested circles became known as a Tusi couple. This is the mathematical system that finds its way into Copernicus's work some 300 years later. Having found a solution to the equant problem, Al-Tusi now wanted to complete the task Ibn al-Haytham had started 200 years earlier, to find a consistent mathematical description of the movement of the celestial bodies. But to do that, he needed better data, which meant bigger and better equipment than he was ever going to find here at Alamut. And then something happened which changed Al-Tusi's life forever: the Mongols. Streaming in from the east, an army of Mongols led by Haluga Khan marched into Iran, crushing everything before them. By 1255, they had reached the foothills of Alamut, intent on its destruction. Then, in a brilliant piece of diplomacy, Al-Tusi managed to both save his own skin and satisfy his scientific ambition. He visited the Mongol leader and played on his deep astrological superstition. Convincing him he could tell the future if only he had new equipment, Al-Tusi persuaded the Khan to make him his head scientist and to build him just a few hundred miles away, perched on a hilltop where the air was clear, the largest observatory the world had ever seen. This is all that remains of the Maraga Observatory. The main instrument is hidden under this protective dome. Al-Tusi's new astronomical center was based around a single large building. Inside was an enormous metal arc, an armillary arm, 10 meters across. On its circumference were marked angles in degrees and minutes. The scientists would line up the celestial object under study with a central point on the arc, and then make a reading from the markings on the arc, giving them the definitive, accurate position of the object in the sky. The building was also surrounded by smaller astronomical equipment, libraries, offices, and accommodation. The observatory even had its own dedicated mosque.
I suppose it is a little disappointing that there's not that much left of the place now. So you really have to imagine what it must have been like back in its heyday. After all, what Al-Tusi built here was nothing less than the world's greatest observatory for 300 years. And like any modern-day international research institute, he brought together the world's greatest astronomers from as far away as Morocco and even China. I mean, it must have been a really great, buzzing atmosphere to work here.
With his new observatory and world-class team, Al-Tusi was now ready to fulfill Ibn al-Haytham's dream, to try to make Ptolemy's model scientifically rigorous. First, they attacked the mathematics. As well as the Tusi couple, they invented other systems of planetary movement. And with these new systems, they were able to calculate mathematically consistent models for many of the celestial bodies. Mercury, Venus, Mars, Jupiter, Saturn, and the Sun and Moon.
Al-Tusi and the astronomers he brought together created what became known as the Maragha Revolution, which was a complete paradigm shift in astronomy, overthrowing the old Ptolemaic view.
What Islamic scholars and astronomers like Al-Tusi do is to organize and make sense of mathematical astronomy at a level of unprecedented accuracy, using instruments more precise than had been built before, over longer timescales, with predictions of the positions of planets and stars that no one had previously reached. That at Maragha or at Alamut, we see, I think, genuine revolutions in the level, scale, and intensity of mathematical astronomy.
But there was still a problem. The new models were mathematically coherent, and they dispensed with Ptolemy's unwieldy equant. But they still firmly placed the Earth at the center of the universe, and that inevitably meant that their descriptions of the heavens were intricate and complicated, with epicycles, deferents, and couples. It was like some great cosmic gearbox. It would require a huge leap of imagination to make the next step in our story. And that next step would take place 2,000 miles from where I am now.
In my view, the last phase of the Maragha Revolution took place not in Iran or anywhere in the Islamic Empire, but here in northern Italy. Based on the work of Muslim scholars, places like the University of Padua were already starting a new scientific movement, the Renaissance.
Back in Padua, where I began my journey, I now understand why Islamic astronomers were so important to Copernicus. They gave him his motivation. He's the first European to share Ibn al-Haytham's deep aversion to Ptolemy's cosmology. And that's what makes Copernicus not the first great astronomer of a new European tradition, but the last of the Islamic tradition.
This is the second edition.
As we've seen, many of the complex mathematical models Copernicus uses in his new heliocentric model, like the Tusi couple, are copied from Islamic astronomers. But more importantly, it's Copernicus's deep desire to bring mathematical consistency to cosmology that he really owes to his Islamic predecessors. Copernicus's ideas set in motion a train of scientific revelations that would eventually lead to Isaac Newton and the discovery of gravity. In Newton's hands, Ibn al-Haytham's dream of an astronomy with rigorous and coherent mathematics, which agrees with experimental observation, finally took place. But this begs two crucial questions. Why was the great astronomical project which Islamic astronomers began completed in Europe and not in the Middle East? And how did knowledge of Islamic science get to Europe in the first place? The answers to these questions lie in one of the most beautiful cities on Earth, the Queen of the Adriatic, Venice. Venice was founded on a swamp off the coast of Italy and felt itself separate from Europe and not bound by its laws and traditions. And as Shakespeare famously pointed out, the two most important aspects of Venice were its merchants and its long-standing links with the Arabs or Moors. It was a rich and complicated relationship, sometimes based on piracy and theft.
The story goes that in 828, two Venetian merchants stole the bones of a famous Christian saint from Venice's rival city across the water, Alexandria. The bones belonged to St. Mark the Evangelist, and they brought them back here to St. Mark's Square.
But without doubt, trade with the East brought to Venice great wealth and an exchange of ideas, customs and people, as Venice expert Vera Costantini showed me.
So this is called Campo dei Mori because, as you can see, at the corners there are statues of what were called Moors.
Yeah. Oh, there's another.
Yeah, there's another one with a turban. The beard was recommended to Venetian merchants even when they went to the East. There were manuals written for Venetian merchants.
How to blend in.
How to, yes, you know, how to be respected in the East.
Yeah. Oh.
As Venetians traded more and more with their Muslim neighbours, the influence of Islam was more strongly felt. Arabic coffee culture became hugely popular, as did Islamic styles of architecture with their characteristic arches and decorations.
So the next thing I want to show you is the Palace of the Camel. When Venetians traded in the East, the unity of measurement of a load that could be loaded on a dromedary was called a carico. And it was the exactly same unity of measurement they had in the East, and it was called yoke.
So it's not coincidence that they...
No, it's not,
that they actually imported that unit of weight?
Yes, of measurement, yeah, of weight.
And with the Arabic trade came the Arabic books. The great 9th century Arabic text on algebra appeared in Latin in the 12th century. The same century saw the arrival of Arabic astronomical tables. And in the 15th century, the famous Canon of Medicine was first published in the West. And this influx of learning seems to coincide with a great historical shift. The engine of science begins to move west, from the Islamic world to Europe. That's where the great breakthroughs from the 1500s would mainly take place. I encountered an astonishing and very tangible symbol of this shift and a really surprising clue as to why it happened, thanks to Professor Angela Nuovo from the University of Udine. "20 years ago, in this library on one of the islands of Venice, Angela discovered the only surviving version of a 500-year-old book."
And what did it feel like? I mean, this is a big
yes.
discovery.
Yes, it was a great emotion. I remember it was July, very hot, like today, even hotter, and I felt cold at that moment, yes. And yes, it was a great emotion.
What she found was the very first printed copy of Islam's holy book, the Quran. This is the first time she's seen her Quran since she discovered it 20 years ago. But it struck me as strange that the world's first printed Quran was produced in Venice and not in the Islamic world. And it's obvious at first glance that it was printed by people who didn't speak Arabic very well.
Bismillah ar-Rahman ar-Rahim. Alhamdulillahi Rabbil Alameen ar-Rahman ar-Rahim. Malik yawm ad-Din. Iyyaka na'budu wa iyyaka nasta'in. Yeah, I mean, what strikes me is that it's
It's written in what I would regard as almost childlike handwriting. It's clumsy.
Yeah. Well, it's the first attempt to reproduce the handwriting in movable types. And as you know, the language has an enormous amount of sorts, different sorts, as, of course, every letter changes according to ligatures and the position
of course. So
in the lines.
The word dhalika, which means for that, the dash should be underneath the L here, but it's above it.
Yeah.
So instead of saying dhalika, it says dhalaka, which is wrong.
Probably there were not people really of mother language in the press. So there were some errors of the mistakes in the text, which are, of course, sins.
Yes, of course. I mean, as the Quran, for every Muslim believes it's this word of God. You
the
can't
word of
change
God.
it.
So when you change it, it's a sin. It's
yes. How was it first received, do you think, when it was published?
Well, yes, the idea is that the hypothesis is, and I think it's true, that it was an enormous failure from really the business point of view, as the Muslim didn't accept the printing press for centuries, and probably the whole copies of this book were destroyed. So we don't have any other copy. Probably the only one that remained in the Western world is this book.
I felt that the failure of this printed Quran to catch on in the Islamic world spoke volumes. "800 years earlier, one reason for Islamic science's success had been the precision of the Arabic language. With over 70 different ways of writing its letters and many extra symbols to define pronunciation and meaning, it allowed scholars of many different lands to communicate in a single common language." Now, with the arrival of the printing press, scientific ideas should have been able to travel even more freely. In the West, books printed in Latin accelerated its scientific renaissance. But because of its symbols and extra letters, Arabic was much harder to set into type than Latin, and so a similar acceleration in the Islamic world failed to materialize. I believe this rejection of the new technology, the printing press, marks the moment in history when Arabic science undergoes a seismic shift. Europe has embraced Greek and Arabic knowledge and the new technology, and Galileo and his ilk are poised at the cusp of the Renaissance.
It has been a turning point both in the history of the Venetian printing press, who used to be extremely powerful. I mean, it's the limit of expansion, let's say, and in the history of the relationship, the cultural and general relationship between the East and the West, as acceptation of printing would have meant the acceptation of the first important technology. So, you know, the two histories started to differ very much, as you know.
This initial rejection of printing was one of the many reasons that caused science in the Islamic world to fall behind the West. It coincided with a host of global changes, all of which affected the way science developed. The first and most obvious reason for the slowdown in Islamic science is that the Islamic Empire itself falls into decline from the mid-1200s. One reason for this is that it's under attack from all sides. From the east are the Mongols.
In 1258, they invaded the capital, Baghdad, and it's said that the waters of the Tigris and Euphrates rivers ran black for days with the ink of the books they'd destroyed. But trouble was also brewing in the far west of the empire. Islamic Spain, already fragmented into separate city-states, now faced a new threat, a united and determined onslaught from the Christian north.
The Reconquest, as it was called, raged for hundreds of years. but culminated in the 15th century when Ferdinand II and Isabella led an army which forced the last of the Muslims in Granada to surrender in 1492.
The Christians were intent on removing every last vestige of Islamic civilization and culture from Spain. In 1499, they ordered the burning in this square in Granada of all Arabic texts from Granada's libraries, except for a small number of medical texts. Within about 100 years, every Muslim in Spain had either been put to the sword, burnt at the stake, or banished.
And Christians from the east of Europe were intent on reclaiming the Holy Land. The Crusades.
Bent on carving out a holy Christian Levant and claiming the holy city of Jerusalem, the Crusaders launched a massive attack on northern Syria. They quickly captured this castle and turned it into one of their strongholds. Then, with ruthless and missionary zeal, they marched on Jerusalem.
And as the empire fought with its neighbours, it collapsed into warring fiefdoms. The Mamluks, slaves who originally belonged to the state of Egypt, became its leaders. The Bourbon Almohads ruled Morocco and Spain in the 13th century, and the north of Syria and Iraq splintered into a series of city-states. But for many historians of science, the biggest single reason for the decline in Islamic science was a rather famous event that took place in 1492. That year, the entire political geography of the world changed dramatically when a certain Christopher Columbus arrived in the Americas.
I explain it with the phenomena of the discovery of the New World in 1492. The immediate result is that you got immense amount of gold and silver coming to the royal houses of Europe at the time, and all the adventurous empires and royal houses of the time who were setting colonies all over the world.
And science always follows the money. As the 16th and 17th centuries came and went, that money, power, and hence scientific will moved through Spain and Italy and on to Britain. By the 17th century, England, sitting at the centre of the lucrative Atlantic trade route, could afford big science. And that ultimately explains why the greatest book in world science, Sir Isaac Newton's Principia Mathematica, the book that ultimately explains the motion of the sun, the moon, and the planets, was not published in Baghdad, but in London.
It was necessary for him to have data of astonishing accuracy gathered from across the world. Global inventories of numbers, observations, positions. The heights of tides, the positions of comets and planets, the rate at which pendulums beat. It's a global project. It's big science. And many of those observations, many of those mathematical models were, of course, models initially developed by Islamic astronomers in Egypt and the Near East and Central Asia.
But there's a final twist in the tale. As the wealth of the Islamic nations subsided through war, political and religious entrenchment, and the loss of its lucrative trade, so its science declined. But what this doesn't explain is why their scientific achievements have been so forgotten. And that's partly because, as Europeans colonized great swathes of the Middle East and Asia, they actively encouraged the idea that the civilizations they encountered were moribund and in decline.
It seems the English and the French were uncomfortable with subjugating people whose knowledge and science may have been as sophisticated as their own. So it became important to portray the Islamic world in a very specific way. Namely that, yes, they once were very sophisticated and they had great scientists and philosophers, but of course now they've fallen into decay. Somehow, this point of view made the whole colonial enterprise seem much more palatable.
One of the most fascinating developments, I think, in the history of the encounter between Western Europeans and other cultures is a kind of shift which has got fundamental and terrible consequences amongst Western Europeans when they start to reflect on why they are superior. It doesn't often cross Western Europeans' minds that they might not be superior to everybody else. For a very long time, after all, Western Europeans in general, the British for example, supposed that their superiority lay in their religion. But then I think around the 1700s, we begin to see a shift. And the shift is from claiming that the reason for European superiority is its religion to the reason for European superiority is its science and technology. Eventually it ends up with the famous phrase, we have the Gatling gun and they do not. Europeans in that period were quite prepared to acknowledge that in ancient times, Islam, for example, had achieved great things in the sciences, but they weren't doing so now. So even recent Islamic and Sanskrit astronomy was imagined to be very old, because if it was very old, it meant that the culture the British were conquering was declining. And for the British, that was clearly good news.
And some experts believe that the effect of this on Islamic scientific history is still felt in the Islamic world today.
The Islamic part and the Arab part have not yet discovered their history because their history was obliterated intentionally by the colonization period. And unfortunately, when they rediscover it now, they're rediscovering it in bits and pieces.
So today, for many different reasons, the great observatories of the medieval Islamic world are ruined husks. And it's true to say that most of the great scientific breakthroughs of the last 4 centuries have taken place in the West. But that's not to say that science has completely ground to a halt in the Islamic world. Now, in the 21st century, there are many examples of cutting-edge research being carried out.
Well, I've arrived at the Royan Institute here in Tehran, where they carry out stem cell research, infertility treatment, and cloning research.
I was surprised to learn that here in Iran, an Islamic state, potentially controversial science like genetic modification and cloning is condoned, even funded by a theocratic government.
One of the uses is when a small part of the heart stops working, which is finally going to lead to heart failure.
Right.
So the cells from that part of the heart are actually replaced with the cells that have been cloned. Another use of cloning in therapeutics is actually creating an animal which has the medicine in their milk, for example. So when we drink the milk, we actually receive the medicine we need.
Considering genetic research has many vociferous opponents in Christian communities, I was intrigued to see that here in Tehran, they have their own in-house imam to offer support and advice on this sometimes quite controversial research.
We have got this medical ethic committee here in Royan Institute, and every project which is proposed is investigated in this committee, and we see different aspects of it, and they have got to justify the project for us.
I'm not enough of an expert in genetics to truly assess the quality of the work here, but one thing I can say is how at home I felt. Whatever cultural and political differences we have with the Iranian state, inside the walls of the lab, it was remarkably easy to find common ground with fellow scientists. Nature's rules are refreshingly free of human prejudice. That's something the scientists of the medieval Islamic world understood and articulated so well. In the 9th century, Al-Khwarizmi synthesized Greek and Indian ideas to create a new kind of mathematics, algebra. The polymath Ibn Sina brought together the world's traditions of healthcare into one book, contributing to the creation of the subject of medicine. In remote Iranian mountains, astronomers like El-Tusi paved the way for scientists working hundreds of years later in Western Europe. These scientists' quest for truth, wherever it came from, was summed up by the 9th century philosopher Al-Kindi, who said, "It is fitting for us not to be ashamed of acknowledging truth and to assimilate it from whatever source it comes to us. There is nothing of higher value than truth itself. It never cheapens or abases he who seeks."
One moral emerges from this epic tale of the rise and fall of science in the Islamic world between the 9th and 15th centuries. And that is that science is the universal language of the human race. Decimal numbers are just as useful in India as they are in Spain. Star charts drawn up in Iran speak volumes to astronomers in Northern Europe. And Newton's Principia is just as true in Arabic as it is in Latin or English. What medieval Islamic scientists realized and articulated so brilliantly is that science is the common language of the human race. Man-made laws may vary from place to place, but nature's laws are true for all of us.
That was the last in the series. Next tonight, how to fit a square peg into a round hole. If only it were that simple. It's Hole in the Wall, next.